All right. So today we have optimization, and then I think Wednesday we do test review, and then next Monday's the exam, right? That sound right to everybody who maybe thinks we have a schedule or not? Let's see.
Sounds right.
Let's ask Cole. What is our schedule?
It is next week.
Yeah, we have optimization today. Wednesday, you turn in your curve sketching and we do the test review. And then next Monday is your third exam. And we're almost done. Oh my goodness.
Flying by.
Feels so good.
Wow.
I have
Wow.
4 essays still though.
Okay. Okay. So today we have, like I said, optimization. Basically, optimization is a fancy word for finding maximums and minimums, which we already know how to do. So what we're going to do is set up the problem, find the formulas that we need, see which formula we need to optimize. So in the problem is going to say minimize this or maximize this. Yes. So we need the formula to work with, and we're going to optimize it. So that means once we find the formula to work with, we're going to take the derivative, we're going to set it equal to 0, and we're going to solve for x. Again, everything we know how to do. Now they're just word problems. So optimization are just maximum and minimum word problems. Okay, and there will be substitutions in here. Okay, and I'll show you what I mean by, let's work the first example. Find the dimensions of a rectangle with an area of 200 square feet that has the minimum perimeter. Okay, so first thing to do is we can draw a diagram. Okay. Oh, angry baby. What? All right. So here's a rectangle, and I'll just label the width y and the length x. Okay. So this says that we have a rectangle with an area of 200 square feet, and it has the minimum perimeter. So we know that the area of a rectangle is x times y, and we know the perimeter of a rectangle is 2x plus 2y. And our goal here is to minimize the perimeter. So we need to minimize this function, this formula. Okay, but remember when I said minimize, that means we're going to take the derivative. Well, we can't take the derivative in this form. So if we happen to do that, I'll show you what happens. So if we said d over dx of the whole equation, well, you would get p prime equal to 2 plus 2y prime. And for this type of problem, we do not need a y prime. Y prime would make this a related rates problem, meaning that the rectangle is changing at some rate with respect to time. And for this problem, this rectangle is not changing. It is not moving at a certain rate. So what we have to do is make a substitution for that variable of y. Okay, so we don't do this. Okay. So now let's go ahead and use the information that they gave us. They said that we have an area of 200 square feet. So here we go. All right. So number one, we're going to say make a sub. Oh, I can't even write. Make a sub. Okay. So using the information from above, they say that the area is 200 square feet. So we get that x times y equals 200. Okay. And now to replace this y in the perimeter formula, we just have to rearrange this one and solve it for y. You'll get y equals 200 over x. And here's our sub. So now we're going to plug this in for the y value in the perimeter formula. Okay. So 2, I'm going to say plug y into perimeter. So we get p equals 2x plus 2 times the new y value of 200 over x. Okay. And now let's go ahead and simplify this. We'll get p equals 2x plus 400. And all I'm going to do here is flip that x to the top, making it 400x to the negative 1. So what we have now is a perimeter formula, a perimeter equation, all in terms of the same variable. So we have this all in terms of x. So now all we have to do is optimize it, which means the problem said to minimize the perimeter. So we are going to minimize the perimeter. Which means we're going to take the derivative of it, set it equal to 0, and solve for x. So we'll say d over dx of the whole equation, p equals 2x plus 400x to the negative 1. And we're going to get p prime equal to 2 minus 400x to the negative 2. And now after we look for maxes or mins, we take that derivative and we set it equal to 0. So now p prime equal to 0, and you get 2 minus 400 x to the negative 2 equals 0. And let's go ahead and solve for x. Move that 400 over. I'll make this 2 equals 400, and I'm going to flip that x back to the denominator. So you get 400 over x squared. Multiply the x squared to the left, and you get 2x squared equals 400. And then divide by 2. And x squared equals 200. Then square root both sides. And x is going to equal plus or minus, and the square root of 200 is 10 square root of 2, or 14.14. Okay, well, since this is a rectangle and we're talking about length, we know we can only keep the positive one. So here, x equals 14.14 feet. And now all we have to do is solve for y. So that'll be step 4. Because in the problem, we're looking for the dimensions that could minimize this perimeter. So this means step 4, find y. And we're just going to use the substitution we made on the left side. So we're going to have y equals 200 over our x value of 14.14, and 200 over 14.14. 14.14 is still 14.14 feet. So if you ever optimize a rectangle, it becomes a what?
Square.
A square. And our dimensions are 14.14 feet by 14.14 feet. And that's how optimization works. So we have to find out what formulas we need. Hopefully we
And
get
that's why
them.
we
We're
need
given
to
them.
out.
Ah,
But I got to buy another one because Jessica wants them and she can't really go out
yes,
and buy
she
it.
does. Okay. All right.
Jessica
So-
gets a mute.
Okay. So again, optimization, get the formula, put it all in terms of one variable, then maximize it, minimize it, set it equal to 0, solve for X, and plug it in where we need it. So any questions on that process? Everybody good? Got the brown thumbs up from Amanda. Perfect.
It's so weird.
All right. Cool. All right, let's do it again. Example 2. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay. So here we need to maximize area. We need to find the largest area. So let's go ahead and draw our diagram again. And we're putting our fence along the river where we need no fence along the river. Okay. Here's my river. And here's my fence. Let's go ahead and label the width Y again and the length X. Okay. Well, we know that the area of a rectangle is still X times Y. The perimeter of this rectangle is going to change. We now have X plus 2Y. And again, it's going to be X plus 2Y because we don't need a side along the river. Okay. And now what we want to do is maximize the area. This is what we want to maximize. But we can't take the derivative of it yet, again, because of that Y value. So we want to get rid of that Y value by making another substitution. And of course, by using the information given above. It says that the farmer has 2,400 feet of fencing. So that means that our perimeter is 2,400 feet. So step 1, we do our sub. So we have that X plus 2Y is equal to 2,400. Now go ahead and solve this equation for Y. You'll get 2Y equals 2,400 minus X, and then divide by 2, and Y equals 1,200 minus 1/2 X. Here's our sub. All right. Now, once again, we're going to take that Y value and we're going to plug it in for the Y variable in the area equation. So 2 plug Y into area. So you'll get area equals X times our new Y value of 1,200 minus 1/2 X. Go ahead and distribute the X, and we get 1,200X minus 1/2 X squared. There it is. There's the area equation. we now have it all in terms of one variable. So go ahead and maximize it, optimize it. So that's step 3. We're going to maximize area. So that means we just take the derivative with respect to x on both sides. And we'll get a prime is equal to 1200 minus x. 1200 minus x. And now we set it equal to 0. $1,200 minus x equal to 0. And 1200 is equal to x. And again, I think this is in feet. Yeah. So x equals 1200 feet. All right. Which means we have found x. And now all we have to do is find y. Which means go ahead and plug it back into our substitution that we made in step 1. So 4 is find y. Okay. So we'll get y equals 1200 minus 1/2 times 1200. And that's going to be 1200 minus 600, which means that y needs to be 600 feet. Okay, there you go. So in order to maximize the area of this fence that will border the river, the length needs to be 1200 feet and the width needs to be 600 feet. Okay. And I think we wanted dimensions again. So dimensions is what, 1200 by 600? And there we go. All right. Any questions on that one?
No questions.
All right. You don't want a thumbs up anymore?
No, you guys seem to have a problem with my brown thumb, so I'm not going to use it.
I mean, I'd rather hear people talk instead of me just thinking Ryan's the only one there.
I'm not here.
All right.
Well, you
I
did-
quit.
I quit.
You did it the
Alright.
opposite way on the other recording.
What'd I do?
Oh, you just flipped the variables, but it doesn't really matter.
Oh, see, doesn't matter. Same thing. I could even, what's cool about optimization is that you don't have to put it all in terms of X. You can put it all in terms of Y and you'll get the same result.
Oh, yeah.
But if your equation is all in terms of Y, let's say it was area equaled Y squared, like minus 1/2 Y or just 1/2 Y, then you would take the derivative with respect to Y on both sides. That's something you've probably never seen. But I mean, you're taking the derivative, so it would work the same way. You'd get 2y minus 1/2. But yeah, as long as you get the equation all in terms of one variable, you're good to take the derivative. Okay. 3, a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So the surface area of a can or a cylinder is A equals 2 pi r squared plus 2 pi r h. And the volume of a cylinder is V equals pi r squared h. And then one last thing we need for this problem is that 1 liter is equal to 1,000 cubic centimeters. Okay. Our job is to minimize the cost of the metal to manufacture the can. So would we minimize surface area or minimize volume?
Surface area.
Surface area. Good. So this is what we need to minimize. But again, we can't take the derivative because we'll get a variable we don't need. You'll get an H prime if you take the derivative. And what an H prime means is that the height of the can is changing at a certain rate. And for these types of problems, these are not related rates problems. So the height is not changing at any type of rate. So this means we have to make a substitution using some given information. Okay. So we know that the volume of this can is going to hold 1 liter of oil. So we're going to use the volume of a cylinder formula to make a substitution for H. Okay, so here's one. Sub. So we have that 1,000 is equal to pi r squared H. So we're using the volume formula. Okay, and now simply enough, solve this equation for H. You'll get 1,000 over pi r squared equal to H. There's our sub, and that's going in for that H value above. Okay, 2. Plug H into surface area. So we have A equals 2 pi r squared plus 2 pi r times our new H value of 1,000 over pi r squared. Okay. And now we just have to simplify. Oops. There we go. And A equals 2 pi r squared plus, we know that this r and that r will reduce, and even the pi's will cancel. So you will be left with 2,000 over r, or 2,000 r to the negative 1. And now here is the surface area equation, all in terms of r, which means we get to optimize it. We're going to minimize it. Minimize area. And since our variables are, we're going to say d over dr of A equal to 2 pi r squared plus 2,000 r to the negative 1. You'll get A prime equal to 4 pi r minus 2,000 r to the negative 2. Okay. And after we take the derivative, we set it equal to 0. So you'll get 4 pi r minus 2,000 r to the negative 2 equals 0. Move the 2,000 over, and you'll have 4 pi r equal to 2,000 over r squared. So we take that r to the negative 2 and we flip it over. Now multiply it to the left side. Multiply it to the left. you'll get 4 pi r cubed equal to 2000. And then divide by 4 pi, and r cubed equals 2000 over 4 pi. And now all we want is r. So what do you do to both sides?
Cube root.
Cube root. And r is going to equal something. Cube root of 2000 over 4 pi. And we get 5.419 or 5.42 centimeters. Okay, so in order to minimize the surface area of the can, the radius of the can needs to be 5.42 centimeters. And all we have left to do is find the height. So put that there. 4, find height. And from our substitution above, h is equal to 1000 over pi times r squared. Well, r is 5.42. And you're going to square that. And if we want to be proper, this is cubic centimeters, and that's just centimeters. And h is going to equal, just type that in, 1000 over pi times 5.42 squared. And we get that the height is going to be 10.84 centimeters. And there it is. So the dimensions for the can, in order to minimize the surface area, we know that the radius has to be 5.42 centimeters and the height has to be 10.84 centimeters. That's double the radius, right? That's cool. Okay. Any questions on that process? We all good?
Yep.
Perfect. Okay. All right. 4. A box with an open top is to be constructed from a square piece of cardboard, 3 feet wide. By cutting out a square from each of the 4 corners and bending up the sides, find the largest volume that such a box can have. All right. And here we are given the volume of a cube because our job is to find the largest volume. So we're supposed to maximize volume. Okay. Pictures, of course. Ooh, let's go. Where's my, let's see, ink to shape. There we go. I'm gonna draw a square. Hey, that works. Let's try it again. Bam. Beautiful. Look at that. I'm good. I am very good. All right. So we know that this square, this box, is 3 feet wide on all sides. Okay. And then we are going to cut a square piece of cardboard from each of the 4 corners. So we are going to take these corners out. Okay. And now this is what we have. Let's see. We have, I'll just do, maybe it'll do it. Let's see. Do it. It's like, I have no idea what shape that is, sir. All right, I got a better idea. Boom. And boom. All right. Okay. All right. So this means that let's go ahead and start labeling things. Let's go ahead and say that whatever we cut out, let's go ahead and label that X. So from our cutouts, those lengths will be X. So this is going to be X, and this will be X as well. So all of those are X. X and X. I just need that. Let's do X and X. And then since we cut those corners out, we also have one other piece, which is the base of this box, which let's go ahead and label that Y. So the base of this box will be Y. Okay. Now we're going to fold the box up, and it's going to have an open top. It's not going to do 3D for me, is it? Maybe I could build it off of that though. Let's see. That, that, and then oh yeah. Good enough. And now we know that the base of this box with an open top is Y, and the height of this box when you fold it up is going to be X. Okay. So there's our diagram. And now let's get our formulas. So first off, volume is given by length times width times height. Well, we know that the length of the box is given by Y. The width of the box is given by Y. And the height of the box is given by X. Put it together and we get X, Y squared for volume. Okay. So our goal is to maximize volume. Our job is to maximize volume. But again, we can't take the derivative in this form because of that Y value. So we need to find out how to make a sub for it. Oh boy, what did I do? We're back in the beginning. Start all over. There we go. Okay. Well, looking at the second diagram, we see that, or we know that the width of the box is 3 feet. So I can make a formula for that. So looking at the second diagram, remember that the width is still 3 feet. So we can say that W, the width, is equal to X plus Y plus X, or 2X plus Y. And since we know that the width of the box is 3, well, we can make a sub for that. So let's go ahead and do that. We'll follow our steps still. So sub, we know that the width is 2x plus y. So we're going to get 3 equals 2x plus y. Now go ahead and rearrange this equation and solve for y. And we'll get 3 minus 2x equal to y. Here's our sub. And we're going to plug it in for this y value into volume. Nope. So 2 plug y into volume. To get v equals x times the new y value of 3 minus 2x squared. Okay. And now, yeah, we probably want to simplify that. So you'll get x, go ahead and FOIL 3 minus 2x out. And that should give you 9. What is that? 9 minus 6 minus 6. That's 9 minus 12x plus 4x. Distribute that x, and you'll get 9x minus 12x squared plus 4x cubed. Okay, so there's our volume formula, all in terms of x, which means we are now ready to maximize. But I guess before I continue, any questions so far?
Nope.
No? Okay. Okay. So then 3, we're going to maximize volume. And we're going to say d over dx of v equal to 9x minus 12x squared plus 4x cubed. And we'll get v prime is equal to 9 minus 24x plus 12x squared. Set it equal to 0. And I'm going to rewrite it with highest power first. 12x squared minus 24x plus 9 equal to 0. And what common factor could you divide out of everything? Or could you factor out?
A 3.
A 3. You'd be left with 4x squared minus 8x plus 3 equal to 0. Okay. And now we can get rid of that 3. So all we have to do is factor 4x squared minus 8x plus 3 equal to 0. Oh boy. Okay, this shouldn't be too bad. Minus plus, so we'll have minus equal to 0. And what are some good factors of 4?
2 and 2.
Let's go 2x. Let's go 2x. What are some factors of 3?
1 and 3.
1 and 3. Let's see if that works. That's 4x squared. That's negative 6 minus 2. That's negative 8. That's positive 3. Whoa. Set them equal to 0, and you get x equals 1/2 and x equals 3/2. Okay. So now all we have to do, well, I think we have 2 more steps actually. We have to find y. So I'll put that out here. find y. And y was equal to 3 minus 2x. But now we have 2x values to plug in. So let's go ahead and see which one works. So at x equals 1/2, you get y equals 3 minus 2 times 1/2, which will give us just 2. And for x equals 3/2, you get y equals 3 minus 2 times 3/2, and that'll actually give you 0. So can we actually have a length of 0?
No.
No. So this guy's out, this checks out. So this means that if x is 1/2, y is 2, and I think all we have left to do is find volume. V equals xy squared. So we'll get 1/2. And remember that this isn't feet, so let's be proper. Put our units times 2 feet squared. So this means that you'll get 1/2 feet times 4 square feet. And the maximum volume for this box with an open top is going to be 2 cubic feet. There we go. Yeehaw. All right. Any questions on that?
None here.
None here. Everybody's good? Let me make it all fit on the page.
Outstanding.
Outstanding.
I'm trying to deal. I already watched this, but I'm trying to deal with AT&T right now. I wanted to watch you do it again, but I chose to do it that.
We're trying to deal with you, Cole. My goodness. We can't deal.
I'm just on hold, so
Oh, great. Student of the year right there, guys.
dude, I've called them like 3 times trying to get an upgrade because it got shipped back to them, and yeah, I'm dealing with that. It's making me annoyed.
I just like the omission. It's like, yeah, you know that thing you're doing, spending time and effort teaching us? Yeah, I'm not paying attention.
Ooh.
No, but I watched this. I wanted to watch it over again, but I'm noticing that he did that a different way than he did it too, because you squared it instead of you just took the derivative with the product rule and chain.
Look at that. The differences. Bam. Did I make it all fit on the page? Sorry. I'm making it fit on the page while scolding Cole. All right. There we go.
I'm paying some attention. I at least noticed that.
There you go. All right. Cool. Well, last one, guys. See, Ryan did related rates. I do optimization. Ryan hates optimization. Okay.
Oh, they're just not fun, man. Like, who cares about optimizing a fence next to a river?
Farmers, hello. Okay.
Yeah, farmers who hire engineers to do it.
If I'm ever single, I'll put that on my farmers only page.
Farmer dating app.
Yeah. All right. All right. 5. Last one. The sum of 2 positive numbers is 16. I wonder what it could be. What is the smallest possible value of the sum of their squares? All right. So this means that we want to know what is the smallest possible value of the sum of their squares. We want to minimize those values. Okay. So what we're given here is that the sum of 2 positive numbers is 16. So x plus y equal to 16. It could be anything, right? And then it says, what is the smallest possible value of the sum of their squares? So we know that that's going to be x squared plus y squared equal to some number, we'll say z. And our job is to minimize the sum of their squares. Okay. But again, we can't do that unless we get rid of y. Actually, let's have fun and get rid of x. Let's put this equation all in terms of y. Why not?
Oh man, don't get too crazy now.
I know. Totally botch it too, right? Sub. We're going to have x plus y equal to 16. And yes, let's solve it for x. You'll get x equals 16 minus y. There's our sub. And it's going in for x. Okay. 2 plug x into sum of squares. So you'll have parentheses 16 minus y squared plus y squared equal to z. Okay. There's our equation. It's all in terms of y. So let's go ahead and just take the derivative already. Yes, we could FOIL it all out, but I think it'd be faster if we use chain rule on this. So 3, we're going to minimize. So d over dy of this whole thing, 16 minus y squared plus y squared equal to z. And first one is chain rule. So you'll get the derivative of the outside. 2 times 16 minus y times the derivative of the inside with respect to y. Derivative of y with respect to y is just going to be -1. Plus 2y equal to z prime. Z prime. And then clean this up. You'll get -2 times 16 minus y plus 2y equal to z prime. Go ahead and distribute that to -32 plus 2y plus 2y equal to z prime. And you get -32 plus 4y equals z prime. Now, after it's all nice and cleaned up, set it equal to 0 and solve for y. You can move that 32 over, divide by 4, and y equals 8. Who would have known? So this means that if y equals 8, then x is also what?
8.
8. Good. So x equals 16 minus 8. So x is 8. And what would the sum of their squares be?
$124, $128.
Right? Because you'd have 8 squared plus 8 squared equal to z. And 64 plus 64 is 128. That is the smallest possible sum of their squares, 128. And that is optimization. Fun times.